Okay, so this is where we I think stopped last time. We saw that just a second. Yeah, we saw a simple example of a two-input AND gate and how to declare Verilog for that. Then, using a two-input AND gate, two of them, we created a three-input AND gate by instantiating the two-input AND gate module two times and making the interconnections between them. So we created a three-input AND gate. And similarly, we can create bigger designs if required. Now this is a structural method of modeling, not behavioral but structural. Why? Because we are actually creating the structure of the design that we require using Verilog language. So there are different types of data types in Verilog, which is called nets, registers, and even parameters. Net is a physical connection between 2 points. So net must be driven by a driver, such as a gate or a continuous assignment. A Verilog code automatically propagates new values onto a net when the driver changes value. So what net is a physical wire. So in this case, temp, wire temp. This is of data. This is net. So wire is of data type net, and the wire will connect 2 points one to another. From this side, there will be a driver. So this output of the first AND gate will drive a certain value, 0 or 1 on wire temp. This will be propagated to this point and it will connect this value here. That is a simple wire connecting 2 points. That's a net. Registers, on the other hand, represent storage elements. So you can store a particular value till a new value is assigned to it, and you can overwrite registers. Well, assign new values to it, or in case you want to declare constants, those are called parameters in Verilog. So you declare the constant or parameter once, and it will not change the value. So that is like a constant. What are the possible values in Verilog? 0, 1, x, and z. 0 is logic 0, 1 is logic 1, x is unknown state. So in case the design any signal there is no 0 or 1, then it might go into unknown state. It should not really happen, ideally speaking. Z is a high impedance state, so that is used typically for tri-state logic. So if you remember tri-state logic from digital logic design, if you have a bidirectional port, the same port is used as an input port and an output port. In that case, at a given point of time, one of the directions is tri-stated or assigned Z. So, for example, a bidirectional port, right now, the current it is used as an input port. So, the output side will be tri-stated. It will be used as an input port. And then, once the input part is done, then the output will be, then we can take some value on the output side of it. So, Z will be used for tri-state logic. Yes, so this is the same slide. Nets are physical connections. It will connect 2 points. It should have a driver. Registers will help us store certain values. Integer internally is a 32-bit register. So we can directly call something as a data type integer, but internally it will use a 32-bit register. Nets, there are different types of wires available. So all of this is of data type nets. Normal wire, tri means it's a tri-state wire. This is a single bit. Or we can have something called wired or tri-state or wired and tri-state and etc. All of this, the rest of the stuff is only used for simulation purpose, very corner case, special situations. In case of design, only wire and in certain cases tri-state, tri will be supported. So you will end up using only wire a lot for design purpose. Rest of the things are used for simulation, that too in very special to test very special situations like wired or wired and etc. Pull up, pull low. So these are very extremely rarely used even for simulation purpose. It's not used for synthesis and design. For synthesis and design, we'll end up using wire, not even try. So there are certain things that are supported in synthesis. A reg which can store a value will be supported in synthesis. That means I can convert this to hardware. Integer, I can declare a certain signal as an integer data type, but internally it's a 32-bit register. So ultimately it's a reg data type, but there is a special data type called integer. So I can call it an integer and save integer values to it. If normally it is a 32-bit data type, if you want, you can control the integer to, let's say, less than 32 bits. So for example, then I cannot call it an integer, then I have to call it a register of, let's say, 8 bits or 10 bits or 12 bits. And then I can store the appropriate value there. Now, if you remember, a 8-bit register, what is the maximum decimal value I can store in a 8-bit register? What we think?
250,
Sorry,
255.
255, correct. So, if I want to store only up to 255 integer values, why declare a 32-bit integer which will internally consume 32 bits? So rather than that, I will declare a register with only 8 bits and assign integer values to it. So the other 24 bits I will be saving in hardware. That is how you can save area in hardware design. But if required, you can declare a certain signal as an integer, which internally will consume 32 bits, and then we can save values in it. Data type time is there as a part of the language, which can store time in 64-bit unsigned format. So time is simulation time, or any in normally simulation time when you run a simulation. Real is floating point numbers. You can have fractional numbers, which will be stored as real or fractional numbers. Real time is a data type which can store simulation time in fractional format. So 15.01 nanoseconds or 20.53 microseconds or something like that. Now, time, real, and real time, these data types are not supported in synthesis. This can be used for simulation purpose, but we cannot use it for synthesis purpose. Nowadays, till very recently, real numbers or floating point numbers were not at all supported in FPGAs. With the latest FPGAs, I can talk about Xilinx FPGA. So there is a special floating point block, or it's a component basically of the technology library. So I can use it directly as a block and then perform certain floating point operations through that block. But there is a very strict method, there is a very strict procedure that we have to follow to make it work. And that too, it will only work with the latest devices. So till very, very recently, floating point was not even allowed in FPGA operations. So now we can do that with the FPU unit in the 7 series FPGA. So, but that those are very expensive FPGAs and very few people use them. But that's something that is available now with the latest devices, and that component is available as a part of the library. So we can use that if required. Only there are certain restrictions, so there are a lot of restrictions with that, and we have to use it exactly as they ask us to use it. Otherwise, it will not work. So normal Verilog will not allow floating point in that case for synthesis purpose. Let's look at some examples. How do I declare a net and how to use it? Now, wire W1 comma W2. Now W1 and W2 each is a single bit wire. I can declare this in one line or I can declare this in two lines. Wire W1 semicolon, wire W2 semicolon, or both declarations in the same line. Wire 7 down to 0. This is how we call it, 7 down to 0 W3. So W3 is a 8-bit wire. The square bracket will tell me how many, it's a vector, it's not a single bit value, it's a vector value of 8 bits. Now a register, reg R is a single bit register. Reg V 7 down to 0 VReg. So VReg is a 8-bit register. So this is how I will declare a multi-bit register as required. Then declaring a memory. Reg 7 down to 0, my memory 0 to 1023. So if you remember memory, there are two key parameters, width and depth. First is the width of the memory. So each location is 7 down to 0 means 8 bits. The next will tell you the depth of the memory. So overall 0 to 1023 means 1024 location, which is called approximately a 1K memory. So 1K is the depth, 8 bits is the width. So 8 into 1K will give me a 8 kilobit memory. and I can call this memory anything I want. So I will call it my memory, or you can give it some other name in Verilog. Read 7 down to 0, my memory 0 to 1023. This is how you can declare a memory. Okay. Any questions on this?
Okay, I have a small question.
Yeah.
So I'm not sure if this is just an example, but if you say 0 to 1023,
Mhm.
does that mean that like one register is 1K of memory? That's what I.
What I mean by this is, now let me just give me a minute. Okay, so I cannot- What I mean by this is the depth of the memory, and this is the width of the memory. So each location will be 8 bits, and such I have 1024 locations. So overall memory will be 8 kilobits, but each location is 8 bits, and I have, so each location is 8 bits means I have 8 columns, 7 down to 0 each location. And such I have location 0, 1, 2, 3, 4, 5, etc. Okay,
Okay.
so
So
and
then the
yeah,
1023 is uh, bits, not bytes, right?
2023 is the number of locations.
Okay, okay.
So it is just what is called the depth of the memory. This is the depth of the memory. That means these many locations are present in the memory, and each location is 8 bits. So how do I get the size of the memory? Depth into width. That is how I get the size of the memory. So that means 1024 is roughly a 1K memory, 1 kilo memory, 1 kilo into 8 bits. So it's a 8 kilobit memory.
Okay.
8 kilobit memory, or you can call it a 1 kilobyte memory, depending on how you want to call it.
Yeah, that was what was confusing because you write the capital B. So I am like, this is 8 bits, not 8 bytes. Yeah. So that's why I was confused. But it's okay now.
Okay. So that is what this means. Just delete it. Okay. Any other question on this? No. Okay. So there are some other examples of registers. For example, I can declare register A, comma B, comma C. Each register A, B, and C. There are three registers, each single bit. I can declare reg 15 down to 0 counter and shift reg. So counter and shift reg, each of them is 16 bits, 15 down to 0. In the language, I can also declare something like this. Reg flops is 8 down to 4. So this is a 5-bit register called flops. But normally nobody uses it that way. If you want a 5-bit register, you can call it reg 4 down to 0 flops. That's typically how you do it. But this is supported by the language, but not advisable. This is how you should do it in case you want a 5-bit register. You can declare signals as integers, as we just saw. Sum and difference, each is a signal of data type integer. So internally, integer means 32 bits. So 32 bits will be allocated to some signal, and 32 bits will be allocated to difference. If you want a smaller value to be stored, then you can control it saying reg 15 down to 0, sum comma difference. So only because we don't intend to save beyond a certain numbers. So 16 bits is what? 64K, 65K, right? So I don't intend to go beyond that. So I will save the other 16 bits in that case. In that case, we cannot call it an integer. We have to call it a reg 15 down to 0, sum comma difference. So some other examples of registers, how it can be declared. Assignment, there are certain rules. A reg may be assigned only within a procedural statement. There are two types of procedural statements or procedural blocks, as we have seen: initial block and always block. A reg can be assigned only inside an initial block or inside a always block, or it can be assigned a value in a task. Task and functions are subroutines in Verilog. We'll see what they are later on. So task is a type of subroutine, function is another type of subroutine. Inside a task or inside a function, I can assign a register a particular value. Anything outside a task or outside a function, outside an initial block, outside a always block, a register cannot be assigned a value. If you do that, you'll get a compilation error, and you have to fix that. Outside the procedural statement and outside task or function, we have to declare that as a wire, not a register but a wire. Wire can be assigned a value, and wire has to be assigned a value outside the blocks. A reg has to be assigned a value inside the blocks. A reg object may never be assigned a value by primitive gate output or a continuous assignment. Primitive gate output means I can not connect directly, or a continuous a gate cannot be connected directly to a register outside the always block, or a continuous assignment cannot be done to a register outside, because continuous assignments are done outside the always block. In that case, I cannot declare that as a reg, then it has to be a wire. Outside the always block, outside the initial block, outside any block, task or function, it has to be a wire. If you have a reg, the assignment to that has to be inside initial block, inside always block, inside task, or inside function. That's a rule in Verilog. Technically, you don't need strings in hardware, because you're supposed to work with hardware at some point of time. But you may have a need to store strings, right? Strings of alphabets. So there is no special data type to do that, but you can declare a register. Each alphabet will be 8 bits. So 255 down to 0, that means 256 bit. Let's say there is a register called buffer. If we have a 256 bit register, I can store up to 32 characters in them, individual characters, or I can combine them. So 255 down to whatever that nearest 8-bit value, then every character will take 8 bits. So final character will be 7 down to 0. Each character will need 8 bits. Why does it need 8 bits? Do you remember the ASCII table? Did we see the ASCII table during digital logic design?
Yeah,
No?
I've seen yes.
You
Yes,
have.
I did.
So if you remember the ASCII table, each character is represented by a 8-bit hex value. Each ASCII character. So that's why you need 8 bits to represent one character. And 8 bits, then depending on how many characters you want to store, you can declare a register of that size and store it appropriately as a string. So let's say you want to declare, let's take an example here. Let's say I want to store hello as a string. So 1, 2, 3, 4, 5, 5 into 8. I need a 40-bit register. So reg 39 to 0 string. One thing to keep in mind is Verilog is a case sensitive language, so it should be all lowercase. And then I can initialize this reg or something like this. So to store a 5 character string, I need 40 bits. So I declare, let's call it my string. I declared a 40-bit register called my string, and then now I can assign this value to string value. Or typically you don't do it this way in Verilog, because this is a ASCII value. So this is just for your understanding. Typically what you will do is you will save the hex values to it. So if you have so basically what we have to do in that case is reg 39 to 0, 39 to what, 32, yes, will get uh, the hex value for h. So let's call it 60, a 61, right? So a b c d e f g h 69, reg 31 down to 24 will be 8 tick h e a b c d e 66, something like that. So you get the idea how we can do it. What I've done is I want to store this. I want to store this string called hello. So for that, it's a 5 character string. So for that, I have declared a register of 40 bits, and each character will be represented by 8 bits at a time in this my string. Uh, Sorry, it should be my string. And then I'm assigning the appropriate hex values to it, which will represent this character for this 8 bits, this character for the next 8 bits, and so on till all the characters are displayed. Okay, so this is how we can store strings in registers in case you want it. In simulation, when you simulate your design, typically by default, everything is shown as binary or hex values. This is called 8-tick H hex 69. So what it does is it tells the synthesis tool or the simulation tool that this is represented as a hex number, but ultimately it's a 8-bit binary number. So 8 bits have to be assigned for this. 8-tick H69, 8-tick H66. That's how you declare it for 8-bit numbers. So hex value means 2-digit hex value for 8-bit binary number. So that is how we can store strings. Any questions on this?
Nope.
None from me.
Then we have parameters, which are basically constants in Verilog. So there are a lot of reasons you would need constants. You can declare constant by calling it a parameter. That's the keyword in Verilog. Parameter A is equal to 2-tick B00. That's how it is pronounced. 2-tick B00 means this is a 2-bit binary number, and 00 is, and that is assigned to parameter A. Parameter B will be 3-tick B010. So this is a 3-bit number, binary number 010, assigned to parameter B. C is equal to 4-tick B1000. So 1000 is a 4-bit binary number assigned to parameter C. So this is 8 in decimal, this is 2 in decimal, this is 0 in decimal. Parameter D is, or you can do it in separate lines. Parameter D is equal to 3-tick B111. 3-bit number, binary number assigned to parameter D. Equivalent decimal is 7. Parameter E is equal to 1-tick B0. So this is a 1-bit 1-bit number 0 assigned to parameter E. Advantages of using parameters is, as if you have done embedded design or any other design, you can declare a parameter once and use that parameter label or that constant label throughout your design or throughout your program. You declare it once and you use it multiple times, so you can always change it one place and it gets reflected throughout the design. For example, parameter red size is equal to 8. This is a decimal value. When I have to declare a binary value, I have to say something tick B, depending on how many bits it is. When I want to declare X value, I have to declare tick H along with how many digits of binary I need, bits of binary I need. If I declare directly, it's a decimal value. For that, I don't have to say tick D or something. If I just say this, it's a decimal value. A parameter reg size is 8, then I can declare a reg with this label. Reg size -1 down to 0 temp. So temp is a register and multiple bits. And how many bits it is? Reg size -1. So 8 minus 1, 7 down to 0. So temp is a 8-bit register. That is how I can use parameter in throughout my design. This can be used even for input and output ports, this label or parameters. So that is how parameters or constants can be declared in Verilog. So this is just an example module. Now everything in Verilog is a module, as we know. Module compare for, this is a comparator. In that comparator, these are my ports. After the ports are declared, we have a parameter called bus width equal to 8. Then I can call the input ports bus width -1 down to 0 A comma B. So A and B both are input ports. It's a multiple bits. How many bit wide? Bus width 8 minus 1, 7 down to 0. So this is a 8 bit. A is the input port 8 bit wide. B is also input port 8 of 8 bits. So I can use this for port declarations also in case it's required. Any questions on parameters? No? Okay. Module, everything is a module in Verilog. Modules and the design, the logic and the interconnections between modules can be done through ports, and all the logic of Verilog for that block is inside the module. But we need ports on the module to connect between different modules. If you want, you can have interconnections between modules through the ports. An input port by default is internally of data type net. A output port can be a net or it can be a register in case you want to assign it inside the always block. So the output port with the same name has to be declared as a register. We'll see a lot of examples for this. And that has to be declared as additionally a register if we are going to assign it inside the always block. Now in-out port by default is always a net data type. So these are data types that are these are implicit data types. So by default this will be net any input port. Any in-out port will also be a net. Any output port by default will be a net. If you are going to assign it inside the always block, you have to declare an additional register for it. So structural Verilog is, we saw some example of structural Verilog when we instantiated our AND gates 2 times. When we used a 2-input AND gate and created a 3-input AND gate out of it. That is called structural Verilog by instantiating the term used is instantiating the gate 2 times or whatever any number of times you need in that case. It can be done in this fashion. And2 is the name of the module that we are instantiating. A0 is the label of this instance. And dot I0, dot I1, dot O are the actual ports of the AND2 gate. Bracket A, bracket B, and bracket out are local signals at the top level. So this is called port mapping or signal connections between the instance and the local design. So the input ports and the output ports of this gate are connected to the local signals here at the top level. It can be done in this fashion, or this is a shortcut method. And to A1, A comma B comma out. So A, B and out, these are local signals. A will go to the first port, which is I0. B signal, local signal will be mapped to the second port, which is I1. And out local signal will be mapped to the port O of the AND2 gate. Though this is allowed, this is not advisable, this shortcut method. You should use this method every time, because in this case, you have to remember that I0 was the first port declared I1 was the second port declared and O was the third port declared. If you interchange this, if let's say I say B comma A comma out, then B will go to I0 input port, A will go to I1 input port, and out will go to O. So in very small designs, maybe you can remember, but in big, very big designs, these ports cannot be remembered. In this case, if I interchange this dot I1 bracket B, if I mention it first and then dot I0 bracket A, it is okay because I1 will always be connected to B and I0 will always be connected to A local signal and O will always be connected to out local signal. So doesn't matter which comes first. The correct port of the module is connected to the correct local signal in the local module, top level local module. So we have to declare the signal mappings or port mappings in this fashion every time. Don't use the shortcut method.
A quick question.
Yeah.
So when you talk about declaring, like for example, whatever you're talking about here, so are you talking about, let's say you are having a two input AND gate, right?
Mhm.
So whatever you're putting here, you're saying like for this two input AND gate, the first input will be like I0 like that, or is that what you're saying, or
Yeah.
are you saying that?
Let me just copy paste a little bit this example from this. Right. So let me. So now this is my other module and two, which I'm going to instantiate here in the separate module. So let's say this is module top, where A, B, and out are my port list. Input A, B, output out, and module. So what I'm doing here is now there is a separate module called top where I'm instantiating this and2 module. This is a separate module, this is a separate module. This and2 module is instantiated under the top module. Top module has three ports, A, B, and out, which is then connected, which should be connected to uh, the and2 ports here, right? Or let me do it. Yeah, you can do it there, doesn't matter. So I can make these connections in two ways. First, I instantiate this AND2 gate and I do a dot I0. Now in this AND2 gate module, the separate module, I0 is declared first as the input, I1 is declared second as the input, then O is declared. This is the order in which the input and outputs are declared for this other module. So with this first instance method, I will never go wrong because I0 has to be mapped to A input, I1 has to be mapped to B input, and O will be mapped to out input. So it is done correctly. Doesn't matter if I say dot I1 goes to B, then dot I0 goes to A, and then dot O. Whichever order I do it, doesn't matter because the right input here will go to the right input here. But if I do it in the second way, second method, I have to remember that first I0 input was declared in the other module. Then I1 input was declared in the other module and then O. So A, B, and out, accordingly I have to declare. If I by mistake say B comma A comma out, then B input will go to I0. A input will go get mapped to I1 input and out will go to O in that order. Is it clear or you have a question?
No, it makes sense. The only thing I think maybe I'm just rushing ahead of stuff is I'm thinking it's like so like in the top module now.
Hmm.
So in my mind I'm thinking, okay, so you already have and module separately,
Mm-hmm.
and you are adding you are adding the and module to top module.
Okay.
That's, that's what I'm thinking. So maybe I'll just give an example. Maybe you want to make a three three input AND gate.
Okay.
So using two input AND gates, right?
Okay.
So I'm thinking that's what I'm thinking. That I think that was what was confusing me. So I'm thinking it's like you are taking one AND gate and assigning it, or let me just say this: assuming you wanted to make, because in your slides there is one AND gate that you made using two AND gates, right?
Yes. Yes. Yes.
Like you made three. Yeah. So how would you do that with what you're doing?
This one.
I think that's why yeah, this one, yeah.
So again, in this example, if you take this example, there are two input AND gate is a separate module, and this is a module for three input AND gate. Now,
Yes.
in this case, we are using the right method. I0, I1, and I2 and O are all these local input and outputs at the AND3 level. Wire temp is a local wire declared at the AND3 level module. Now I am going to instantiate the two input AND gate two times and do the connections to the three input AND gate input outputs. How? First two input AND gate I am instantiating here. I am calling it A0. Dot I0, dot I1, and dot O. These are the ports of the two input AND gate declared in the other module. And bracket I0, bracket I1, and bracket temp. These are ports or local signals at AND3 module level. That is how I will make the connection between this AND gate input outputs and this AND3 input outputs or local signals. Then I will instantiate this AND gate, two input AND gate second time. I will call it A1 because it has to be a different instance label. Then dot I0, dot I1, and dot O again are input outputs of this AND2 gate. These are connected to bracket I2 means local signal, local input I2. Temp is bracket temp means local signal wire temp, and dot O means local output O at AND3 level.
Yes. Now it makes sense to me.
Now, if we don't do it this way, and I directly say in AND2 A1 I2 comma temp comma O, without doing the dot IO goes to I2, dot I1 goes to temp, or dot O goes to O, then in that case I have to remember that in the other module, I0 was declared first as an input, I1 was the second input declared, and O was the next output declared. I have to remember that if I don't use this bracket method. In very small designs I can maybe remember, but when you take big designs where you have hundreds of input output ports going between blocks, this is very difficult to remember if we don't do this in this way. Dot I0 will go to the local signal I0, dot I1 of the AND2 module will go to I1 of AND3 module, dot O of AND2 module will go to the temp local signal. So this is the right way of doing instantiation of modules and doing the port mappings. Okay.
This makes sense to me.
Yes, so we'll go forward. So that's it. That is what we are doing. And see, this is a simple AND gate. So maybe you are thinking, what's a big deal? But if you take very big designs now, there will be many modules which are instantiated, and they will be connected with each other, and some logic. So all you take a very big hierarchical design. So it will not look as simple as this. There will be a lot of things going on. So you have to make sure that this kind of port mapping is done. So there are no mistakes in the port mappings. This connection of local signal to the, this is called formal, this is called actual. Inside the bracket is actual, means local signal. Dot I0, dot I1 and dot O are the signals inside AND2 module. They are called formals. Formal and actual mapping is correct. So we have to make sure that the local signal is connected to the right port of this instance. Local signal number 2 is connected to the right port of the this instance, and same thing with the third port. So for bit designs, this is the way to go. And since you're starting out, make a habit of using this and not this shortcut method. A module is a principal design entity in Verilog, which means that anything that happens in Verilog happens inside a module. Nothing happens outside a module. Module can have a module name, can have port list, can have definitions of ports. It can be input port, output port, in-out ports. We can have local wires. We can have local registers for this module. We can have local parameters for this module. A module can instantiate other module, like we just saw. Instantiate means create a copy of it. Then module can have its own statements and constructs. So what are some of the statements allowed in the module? We can have an initial block inside a module. We can have an always block inside a module. We saw that tasks and functions are subroutines which can be declared inside a module. All of this is inside a module, between module and end module statement. Module, end module. Everything happening inside this block. And you can have multiple such module for different logical blocks. But module is the key part to it. So let's take an example. Let's say I'm trying to create a 4-bit adder. So I can create a 4. Now this is on the right, bottom right, you'll see this is a digital circuit for it. This 4-bit adder, I have two numbers, A and B. Each is 4 bits. Means A3 down to A0, B3 down to B0. So it's an adder. So, and it's a full adder. So it will generate two outputs, sum out and carry out. Since it's a full adder, I also have carry in as an input to the first stage. Single input carry in, single bit carry in, single bit carry out. 4-bit sum output. So this is my adder, and these are four. These are each is a single bit adder, and I have 4 such adders connected to each other to make it a 4-bit adder. Now this 4-bit adder digital circuit I am going to describe in Verilog using structural method and behavioral method. We'll see what the structural method is. Module add 4. Since you have to name the name, you have to call the module appropriate name. So it's add a 4-bit adder. So add 4. A, B, C, I, bracket A, B, C, I, S and C3 is my port list, out of which A and B are input ports. Each of them is 4 bits. Ci is a carry in, is an input port, single bit. Sum is an output port, 4 bits, 3 down to 0. C3 is a final carry out. Final carry out is single bit output port. Then I have a CO, which is a local wire declared as a 3-bit wire. So 2 down to 0 means it has 3 bits. I'm going to instantiate this single bit adder 4 times. Add, so 4 times means 4 different instance labels. Add A0, A1, A2, A3. Let's take add, then A0, the label for the first instance of the adder. Dot CO, now this is what we're looking at here. Dot CO goes to 0th bit of CO. Dot S goes to S. S is a 4-bit vector. 0th bit of S. Dot A goes to 0th bit of A. Dot B goes to 0th bit of B. Dot CI goes to CI. What this means is, now this adder, this add block is declared here. Sorry, this is a single bit adder declared here. So this module will be instantiated here in the 4-bit adder block. And internally this is a single bit adder. So this is how it looks like, where A plus B plus CI will give me a full bit adder. This module is instantiated here and it has 5 inputs. So CO carry out goes to 0th bit of this wire. CI goes to the CI of this adder. B0 is connected to, or 0th bit of B is connected to the B input of the adder. 0th bit of A is connected to A input of the adder. 0th bit of S is connected to S output of this adder. And 0th bit of CO wire is connected to CO carry out. So 0th stage. Now I will instantiate the adder one more time. The carry out of the first stage goes as carry in of the second stage, which is carry in here. Now if you see here, this is a shortcut method used. So here I know carry in is declared last. So carry out of the first stage or the zeroth stage becomes carry in of the first stage. Then B input. So this is the first stage. So first bit of B vector. Then A input. So first bit of A vector. Then some output. First bit of some vector. And CO, which is a wire. First bit of wire CO. Now this is second stage. I'll instantiate the adder one more time. Call A2. This carry output from the first stage becomes carry in for the next stage. Here, carry out of the first stage becomes carry in for the next stage. So CO1, first bit of CO wire becomes carry input here. Then B input, which is second bit of B. Second bit of A. Second bit of sum. Second bit of CO wire. This is second stage. Now I have to instantiate it one more time because it's a 4-bit adder. Instantiate it, give it a label called A3. Carry out of the second stage becomes carry input to the third stage. Then third bit of B as an input, third bit of A as an input, third bit of sum as the output, and C3, which is the final output, is mapped to the carry out of the third stage, which is this. The carry out of the third stage goes as C3, which is the final carry out. So since this structure is over, I will end the module here because there is nothing else to do. But this add that you see here is declared as a separate module called add, which is a single bit adder. Now this single bit adder has 5 ports, 2 outputs and 3 inputs. This is called a continuous assignment because it's also outside the always block. The syntax is assign curly bracket CO comma S is equal to A plus B plus CI. This will implement a 1-bit full adder for end module. And this 1-bit full adder, 4 of them will be instantiated. This single bit adder will be instantiated 4 times, and these interconnections will be done to create a 4-bit adder. So this is called a structural modeling method. Why? Because I'm creating the structure of this 4-bit adder using Verilog manually without depending on the synthesis tool. All this structure is created manually. Okay, any questions how single bit adder is done, 4-bit adder is implemented?
Not from me.
No.
No questions? You understood this, how it's working?
Yeah.
Okay. So the same adder now can be described using behavioral technique. So how do I do that? This is again a adder, full adder circuit. There are 3 inputs A, B, and C. I carry in. There are 2 outputs, sum and carry out. So I am going to use or implement this adder using behavioral modeling method. How? Let's look at that. Module F adder 4. F adder 4, it's a full adder 4 bits. Sum C out A, B, C, I. This is my port list. Out of which sum is the output port 4 bits. C out is output, carry out is output port single bit. A and B are input ports, each is 4 bits. CI carry in is the input port single bit. I'm going to declare a reg called sum, which is same as the output, 3 down to 0. And reg called cout, which is the same name as the output, as separate registers. Why? Because I'm going to assign them value inside the always block. If you remember a few slides ago, if you're going to assign a value to the output inside the always block, it has to be declared as a separate register with the same name and the same width as the output port. So since I'm going to assign values to my output ports inside the always block, the same register with the same name and the same width has to be declared at a module level and then use it for assignment purpose inside the always block. So registers are declared, local registers, always at A or B or CI. This is my sensitivity list or activation list. Means what? Any change in A signal or any change in B signal or any change in CI signal, the always block is triggered. So this is the activation list or the sensitivity list. Begin the always block. Always block should always have a begin and end to create a block of statements. Sum is equal to A XOR B, A cap B cap CI means A XOR B XOR CI. This is the this is the logical equation required to implement a sum out, as you can see in the digital circuit here, right hand side. C out, which is a carry out, is implemented using these equations. As you can see here, carry out is all the three inputs combined, ANDed, and then finally OR. So A and B, B and CI, CI and A, they will be logically OR, and finally you get C out. And will implement the AND gate. This pipe sign will implement the OR gate. So A and B logically OR with B and CI logically OR with CI and A. This equation will give me C out. So sum and C out, two outputs are generated. End always block end module. I can do that, or I can replace these two statements with a single line. This is another way to do it. Bracket C out, parenthesis C out, comma sum is equal to A plus B plus CI. But let's forget it for now. Let's do this. I'll actually remove this so there is no confusion. So here what we are seeing is we are describing the behavior of a full adder using a always block. So that is why this is called a behavioral method of modeling, a behavioral method of design. We declared the input output ports, we declared local registers, which is the same name as the output ports, because I'm going to use this for assignment inside the always block. And then I'm describing the behavior of the adder inside the always block. End always block, end module. Any questions on this slide?
Maybe just to, maybe I would like to, I didn't get this, I mean, the reg sum and reg count. I already see we have output of sum and out, but I didn't see how we use it down here at the always.
It is using the name association. The name of the register and the name of the output is same, and Verilog is a case sensitive language. So some reg sum and output sum will be interconnected with each other. Is that your question or something else? So when I assign a value to reg here, the reg output will, the reg value will also be connected to the sum output.
And I think Fahad's mic is on, is interfering. I couldn't hear a few steps.
Yeah, Fahad, can you mute your mic for a second? Yes, thank you. So is this what you were asking, Brunil? Brunil?
Yes, that's what I was asking.
So since we are using the same name, if I assign a value to the sum register, it will get assigned to the output port also in that case. Same with C out.
Okay.
Now, if I call this something else, then you have to do additional associations there. But always use the same name for the output port for the registers as the output port. So you don't need additional statements. You can directly assign it inside the always block and then it gets assigned to the output port. If I don't declare those registers, then and that means I'm trying to directly assign to output sum inside the always block and to output C out inside the always block. That is not allowed as per Verilog language. So I have to declare a separate register with the same names and then assign those inside the always block. That's how Verilog works.
Okay, got it. But this is only for the always block, right? So if we are using the other type of description, then we don't need this.
Yes. Now this was continuous assignment for single bit adder that we saw in the earlier slide. Here inputs and outputs are direct ports, and I can, using a continuous assign statement, there is no always block here. The continuous assign statement is outside the always block. Curly bracket CO comma S is equal to A plus B plus CI. I can do this same thing here. Instead of always block, I can say assign curly braces C out comma sum is equal to A plus B plus CI. So, but that is technically
Okay.
this falls under falls under structural description, and technically this falls under behavioral description.
Okay. I'm good.
Yes, but in now this is a small circuit, so you can differentiate between structural and behavioral. When you design big circuits, which is what you will do later on, you will end up mixing all this stuff. You will use behavioral. About 90% of your logic will be declared using behavioral, and even the continuous assigned statements we kind of club under behavioral grouping nowadays. So behave this continuous assigned statements and behavioral description will make up around 90% or maybe even more percentage of your entire design. Very rarely and in very corner case situations, special situations, you will end up using structural modeling methods. Structural modeling method most of the time is used for IP cores. IP cores, if you remember, are small designs which you can buy from some other company or license from some other company, and they are licensed, or you can purchase or license them in two formats. You can get a netlist. This looks like a netlist in Verilog, so you can get it in structural format, or you can get it in behavioral source code format. Obviously the behavioral source code, if you can, this is much more readable and understandable, so you can, if you buy it in this format, you can make changes. So this costs more if you're going to purchase a IP core in behavioral source code format. If you are willing to pay less money, then they will give you a structural format netlist for that IP core, which can only be integrated. Now this will be a very big netlist, so it cannot be understood properly what's really happening. So all you can do is integrate it in your design and just give the inputs and it will generate some outputs for you. So this is structural modeling method used very rarely. The continuous assigned statements and behavioral modeling method will be used 90+% of time when you do Verilog coding for design purpose. Okay, so what's the time? Do we have time? We are out of time. So any questions on this? Any other questions?
No.
Not
So
from me.
so we'll stop here today and then we will continue Friday same time. Yes, okay.
Okay, thank you, sir.
Okay, bye bye. Have a good one.
All right.
Yeah.
You too. Goodbye.